Okay, lesson 4.5, derivatives, application derivatives, shapes of graphs. We're going to be using first derivative tests and second derivative tests to help us analyze the shape of a graph and its characteristic, whether it's increasing, decreasing, concave up or down. And again, it's the analysis of the behavior of a function using derivatives and putting those relationships together. Now, with technology and functions, we can graph them and we can see that, but we still focus on the idea of how those derivatives, the first and second derivative, relate to the shape of a graph. So we first take a look at something related that comes from the mean value theorem. And if you can go back, it's corollary 3. It discusses, as we see a function's increasing, what do we know about its derivative, right? The rate of change is increasing, the rate of change is positive, the function's increasing, the slopes are positive. So we can then make some general statement around if the derivative is positive over some interval, we know the function's increasing. Even though you can take a look, these shapes are slightly different, the derivative is still increasing. We still have positive slopes. One starts slow and then increases, one increases fast and stops and then gets slower. The same can be true if the derivatives are negative, right? When you have negative derivatives over some interval, the function is decreasing. In those shapes too, you could be decreasing slower and then faster, or faster and then slower. Either way, we have increasing or decreasing functions over some interval based off of the derivative of function. So we don't even need to know the values of the function. We can just look at those derivatives. Now, here's a graph of kind of an overall function with different characteristics, and looking at how a function is increasing or decreasing. You can see along a point, the slopes are increasing here. Might want to annotate a little bit. Let's see. Right, we can see here the slopes are increasing, and I like to draw a little, when we have to analyze different graphs, I like to draw little symbols on the little plus symbols to represent the slopes of the line. See, it's increasing and then these are decreasing negative. I like to mark them up. And then once you hit these values here, you have these critical points at these locations for these x values. And then you have a max or minimum as you increase there. Now notice on this one, we have it decreasing, 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 and then a minimum, the slope is 0. You have a horizontal tangent, and then it's increasing, 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 increasing. Now this one starts to slow down, still a positive slope, and then it gets 0 again, and then increases again. So that's neither a max nor a min here. This is going to be called a point of inflection, as we learn later. But again, notice again around the values of the slopes and how then that is related to the derivatives and whether a function's increasing or decreasing. Let's continue on. This leads us to summarize kind of these results into the first derivative test. Here are our 3 kind of descriptions here that we want to be able to keep in mind as we look at the first derivative. If the first derivative changes sign from positive, changes sign from positive when x is less than c to negative when x is greater than c, then f of c is the local maximum. Again, let's draw that out real quick. Let's think about, here's a graph, here's c. If it changes signs, so if f changes sign from positive, meaning that it's increasing, right? It's increasing. And then after c, so this is less than c, this is greater than c. Once we get past c, then the derivative changes to negative, then this has to be a maximum. So hopefully that makes some sense to you, as you can see in the picture, right? If I'm less than c, it's increasing, greater than c is decreasing, this has to be a maximum value. And then the same can be said again, if it's decreasing and then increasing, then this has to be a minimum. F changes signs, F prime, meaning that it goes from negative to positive. Now, if f prime has the same sign, then f of c is neither a local max nor a min, right? That it stays the same. It continues to increase. And that was an example we saw in that other drawing here, where it was increasing, and then increasing. So this is neither a max nor min. And so these are the summarized ideas of the first derivative test that we're going to apply. You're going to follow this problem solving strategy, and it's always about finding the critical points, right, where the derivative is equal to 0 or undefined. And then you want to analyze around that, and we'll see that in a solution here. So here's an example where we found the critical points, right? And then you'll end up having to do some algebra to find those critical values over some interval. Now this is a polynomial, so the domain is negative infinity to positive infinity. And then what's happening is, you see a table up and down. I like to also maybe represent this table from side to side. Like, so here are the values. We have critical values at where we're critical. Therefore, critical points are at 3. So here's 0, 1, 2, 3. So I know there's a critical point there, and at -1. And so that means that I'm breaking up the interval into 3 kind of groups, into 3 regions. I need to check values over here that are from negative infinity to -1. I need to check values in between -1 and 3. And then I need to check values from 3 to infinity. So you substitute into the derivative to find is, I don't need to know what its value is. I just want to know if it's positive or negative. And then that will tell me if the function is increasing or decreasing over that interval. Now, again, we have calculators to graph that stuff, so you'll see it. So you'll be able to confirm that stuff using technology, but you want to be able to apply it and show me you can apply the first derivative test to find if a function is increasing, decreasing, and then whether it's a max or min, right? Because if it's positive or the negative then positive, right? And it has nothing to do, right? I have negative values here. Where the graph is, it's if it's decreasing or increasing. So that would be, again, using the first derivative test. And again, many times you get some weird algebra, and when you're looking for critical values, again, when you end up with something like that, when you cross multiply with that 0, you end up just having to evaluate when the numerator is equal to 0. And you also want to evaluate when the denominator equals 0, right? Because that would be 0, it's undefined at 0. So you want to be mindful of that when you're solving and checking. So once you have those critical values, once we find the critical points here, 0, 1, and -1, you have to break up the region from negative infinity to -1, -1 to 0, 0, and you're checking values and looking for the signs. And then that tells you whether the function is increasing or decreasing, which then leads us to being able to determine if there's a maximum or minimum value. So the function was, you can see here, I'm not going to, you had it from -1, 0, 1 was the other one. So from negative infinity to -1, I know the function's decreasing. Then from -1 to 0, it's increasing. I don't know what the values are. And then from 0 to 1, it's increasing still. And then from 1 to infinity, it's decreasing. So you're going to have a minimum here and a maximum. And then what we're going to learn is some point of inflection here as we get there. So again, that's how we use that information there. Let's continue on. There's the funky looking graph for this one here. Again, because of this weird, you have this funkiness here, and you see this vertical asymptote here, and that undefined at 0. And that was where we had at that 0 increasing, increasing. I would just sketched it out, but you can see now the exact graph, what that looks like. Where that leads us to another aspect of the graphs are concavity. Concavity is the shape, the bend, that bend of it. And that's really determining whether the function's not just increasing or decreasing, but how it's increasing or decreasing. It's the idea that if it's concave down, that or concave up, that you see that we have a slow increase and then it bends. There's that bend, which means the rate of change increases, starts to speed up. Imagine you're walking, you're going, and then you speed up. Concave down, minute you have it increasing, and then you start to slow down, it levels off. And so you have that bend versus the steep increase. And that's what we're talking about, concavity. The derivative is increasing. It's not that it's positive, but that it's speeding up. And you can see in these graphs here, concave up here, that there's this quick, you can see the bend and the way the bend is, and then it levels off. So imagine again, we're looking at the rate of change. Is the derivative increasing or decreasing? So that leads us to test for concavity, or the second derivative test. So if the second derivative, right, the derivative of the derivative is greater than 0, then it's concave up. If the second derivative is negative over some interval, then it's concave down, because we're looking at the rate of change of the interval. Now we have something what's called an inflection point when concavity changes. So that's up, concave up. And look at this notation here. And then here, this inflection point, concavity change. I was up and then negative. And the way we kind of say, can it hold water? So here is concave up, right? It's concave up because it can hold water. Concave down, that if I poured water in it couldn't hold it. And that's an idea of concave up. Concave up holds water. You can imagine some water be held. Here, there's no water to be held. If you poured water into it, it'll just spill off to the sides. This concave up and concave down idea. So as we look at this test for concavity, again, you can then see we're going to look at the sign of the second derivative. So to determine concavity, we need to find the second derivative. The first derivative, right, you find, and then you can find the second derivative. So you end up finding a critical value for the second derivative. The function changes concavity. It occurs either when f prime double prime equals 0 or f double prime is undefined. So important piece right there as we're thinking about it. So you find the second derivative, set that at equal to 0, and that's what will tell you whether there is a change of a concavity or a potential point of inflection. So you can see concave down, concave up. And so this is an important summary table to help us determine if a function is concave up, increasing, decreasing, and look at the relationships between them. And you would want to draw them out. So I would stop and analyze this from our textbook here. The shapes of the graph, what's happening with the derivatives, the first and second derivative in those intervals, and then what happens whether you have a max min value, where there's concave up and concave down. And that's what kind of summarizes our second derivative test, where you're checking to see, suppose f prime is equals 0, f double prime is continuous over an interval containing c. You then have these things to determine if f double primacy is greater than 0, then it's a local minimum. Think about it, it's concave up, it can hold water. Concave down, it can't hold water. So it's one of those that has like the maximum where the water doesn't hold into it. And then f double prime of c equals 0, that means it's inconclusive. We don't know if it's a max or min or what's going on. It could be undefined, it can be a point of inflection where, right? So again, you'd have to then further examine that. As you see in this example, you have the first derivative, the second derivative. And so when you solve that, this table here, you evaluate the second derivative, each of the critical points, right? So you have these critical values here that come up, and then you evaluate the second derivative to determine if it's a local, because it's negative, a local maximum, positive. Again, it has to do with the shapes of those graphs, why we have that. So when we look at, again, when you plug into the second derivative, right, and it's negative, that means it's concave down, sorry there. Concave down, which doesn't hold water, so you're gonna have the maximum. When the second derivative is positive, it's concave up at that point, which means there'll be a minimum value there, or versus a maximum. So again, make sure you read those examples there or get those videos so you can take a look at how we apply the first derivative test and the second derivative test, and you'll see you're going to want to make sure you know those skills. It's a classic final exam question, applying first and second derivative to most of the time some polynomial or some function where you can solve for critical values.